take an example where we have some character strings. Okay, let's say this entire sequence that I have here is arising as a character string. So it's like it could be a large molecule like a DNA sequence. So in that case, these Xi's take 4 possible values, the 4 nucleotide bases. Okay, or it can be some other character string. Okay, so this entire sequence is a large character string, and then I am copying or replicating that string, like this DNA molecule is getting replicated. Okay, so it gets replicated, and I produce another string Zn. So this is like just a copy of X. So in ideal condition, this Zi should be exactly equal to Xi. Okay, so there is no change. Okay, but what can happen sometimes is that as you make the copying, some error occurs, which in the language of biology calls mutation. Okay, some mutation may occur. So originally there was maybe X1 equal to something that gets changed. Okay, so let's say I have all these Xi's take values in some set A. So A is a finite set, say a finite set. So all these Xi's are taking values in that set A, and there is another process. I'll denote that by, let's say, which controls the copying mechanism. Okay, so if Wi is equal to 1, then you just copy Xi to Zi. You don't alter it. But if Wi is 0, then you might alter it. And then the alteration will again happen according to some probability model. For example, suppose in the original Xi was alpha, and then you choose some beta from the complement of alpha in A to create your Z. So if Wi equal to 0, then Xi, then Zi becomes some beta. And if Wi is equal to 1, then Xi equal to alpha implies Zi is also equal to alpha. So no mutation or no change. Okay, so it's a complex replicating process that we are trying to model now. Okay, so you have a sequence W that controls the replication mechanism, and you have this sequence X, which is the original sequence. Okay, so what is this Zi going to be? Essentially, if I know Xi and Wi, I can write down what Zi is going to be, right? So Zi is essentially a function of that. Okay. So if I use some Markov model for the original sequences, these Xi's and Wi's, then this Zi is again going to be a function of a Markov chain. Now this model arises in biology in a slightly different name. Anybody knows what it will be? So you have an underlying Markov chain. So it's like you take this chain, so you pair them, you take this chain, and then depending on Wi equal to 0 or 1, you have to choose a character from A according to some distribution, and then that creates your Zi. You recognize this model? Some of you who might have seen Markov chain or some extensions of that. It's a hidden Markov model. Very good. It's a hidden Markov model, right? So all of you recognize this as a hidden Markov model. There is an underlying Markov chain, and that underlying Markov chain determines what will be the observed chain, and then there is another distribution that plays the role that distribution really the distribution that I am talking about here. So when Wi is 1, then xi equal to alpha will ensure zi is also equal to alpha. But when Wi equal to 0, then you have to choose this beta from this set according to some distribution, so there is some randomness involved in that also, okay. But what have I said just before introducing this word hidden Markov model? I said that this zi is going to be a function of a Markov chain. So essentially I have given you a proof. You can now formalize that any hidden Markov model is actually a function of a Markov chain. You can represent a hidden Markov model as a function of a Markov chain, okay. So earlier you have seen any k-step Markov model is a function of a Markov chain. Now you have seen that hidden Markov model is also a function of a Markov chain, provided you write down the underlying Markov chain properly and write down the function properly. So hidden Markov model is also a function of a Markov chain. So if you want to study hidden Markov model, that's equivalent to studying functions of a Markov chain. In fact, functions of a Markov chain were studied much earlier, okay. They are almost as old as the theory of Markov chains, okay. But the hidden Markov model is a relatively new concept, okay. And this connection is not always made by the people who work on these areas, okay. So there are a lot of interesting results on functions of Markov chain. They are available in the probability literature. And when people study these functions, hidden Markov model, sometimes they end up reinventing those results, okay. Those results will actually follow from the theory of functions of Markov chain, okay. So functions of Markov chain is a very widely applicable tool, okay. So when you are modeling a sequence, almost anything can be covered by functions of Markov chain, and I will show you that why, okay. So let's now see that more general result.